Hi everyone. This is Dr. S. Venkateswarlu, working as a professor of EC at IARE, Hyderabad. Today we will be discussing about DTS, discrete time signals. In discrete time signal, so already we have seen that CTS, continuous time signal. So here we will implement that DSP, digital signal processing. We require both continuous time signal and discrete time signal. So that's why we are entering that DTS, discrete time signal. So under DTS, we require that all sampling. The sampling is the acquisition of the values of CTS, continuous time signal, that discrete points in the time. So with reference to this, what do you call the sampling? The sampling is the acquisition of the values of the continuous time CTS at discrete points in the time. So we can consider that where CTS, already we know that if it is CTS, continuous time signal, it is followed by denoted by x of t is a continuous time signal. Where if you want to consider that we are entering the DTS, discrete time signal, it is denoted by x of n, where x of n is the discrete time signal. So with this, where x of n is the discrete time signal, that discrete time signal is equal to x of n into ts. Okay, where ts is the time between the samples. So already we have seen that samples, like you can consider this all samples t versus x of n, x of t. So either we are to verify that number of samples with this sample. Okay, we have to consider that DTS, representation of DTS and CTS and so on. With this, where DTS, discrete time signals, it is followed by x of n is equal to x into n into ts, where ts is the time between the samples. Okay, so in this, DTS, discrete time signals, can be defined in a manner analogous to their continuous time counterpart. Already we know that where x of t, that is nothing but a CTS, continuous time signal. That x of n, discrete time signal, x of n is equal to a into sine of 2 pi n by n naught plus theta. Using this mathematical expression for that DTS, discrete time signal, can be defined in a manner analogous to their continuous time signal part. It is followed by x of n is equal to a into sine of 2 pi n by n naught plus theta. Here where x of n is a into sine of 2 pi f naught into n plus theta. Okay, so with this, where x of n is equal to a power n, so it is varies that on where DTS x of n is equal to a power n. So here in this case, we know that all n value, where n is the discrete time. Okay, so a also we know amplitude. With this theta, where theta is the phase shift in radians. Okay, so where n naught is equal to discrete period of the wave. Okay, so like this, if we are to know that all n, capital N value, reciprocal of that n naught 1 by n naught is equal to, it is also equal to that f naught. Okay, the reciprocal of this n naught. So it is also equal to that this one, where it is nothing but what you call a discrete frequency. Okay, so this discrete frequency. Okay, here the discrete frequency and what you call discrete period of the wave and phase shift radians within this based on that amplitude, how it is varies the amplitude with reference to that time, the discrete time. We have to consider that all where a discrete time sinusoidal signal, after that discrete time exponential signal. So here by using this precedence rule for discrete time signal, where n versus here that n versus x of n, where x of n is, where it is nothing but DTS, discrete time signal, n versus x of n. So that n value is given, say for example n is equal to 1, 2, 3, 4, 5, 6 and so on. N is increasing, and here also origin that 0, where n is equal to -1, where n is equal to -2, n is equal to -3, -4, -5, -6 and so on. Okay, with this there is a rule for a discrete time signal where n versus x of n. Using this solver, it is assigned that where n is equal to 1 to up to 6 or -6 and so on. Okay, so here in this case, if it is v of n is equal to x of n plus 3, so easily can represent that all this discrete time signal, where y of n is equal to v into 2n, easily can represent like this, what you call graphically for a discrete time signal. It is all are based on precedence rule for the discrete time signal. Okay, with this, so we can consider that all a period. So we know that all if you are using this CTS, continuous time signal. So what is varies that continuous time signal and discrete time signal. With this discrete time signal, based on this continuous discrete time signal, is you can observe that all. If you are using this what you call one cycle, positive half cycle, negative half cycle, and so on, cycle to cycle, we are ready to observe that period. Okay, with this all periods, we are ready to verify that n is n versus the period and so on. This is the discrete time sinusoidal signals. Okay, say for example, discrete time sinusoidal signal, a pair of sinusoidal signal with a common angular frequency is defined. It is followed by what you call of they are defining where x1 of n, right, to define because of it is the DTS, discrete time signal, and second one is where x2 of n. Okay, where it is assigned that first signal what you call sine 5 pi n, because of this discrete time signal, where it is what you call x2 of n is equal to x2 of n is equal to square root of 3 cos 5 pi n. Okay, so using the simple example, because of they are given that are two signals, the pair of sinusoidal signal with common angular frequency is defined. It is based on that it is defined x1 of n and x2 of n. Both x1 of n and x2 of n are the periodic. Find their common fundamental period, and next one is what you call express the composite sinusoidal signal, that is y of n is equal to, how they are using that, where y of n is equal to x1 of n plus x2 of n in the form of y of n. So that y of n is equal to a into cos of omega n plus pi, and evaluate the amplitude a and phase. Okay, with this what do you call, where and this particular example, right, to solve this one, what the relevant to the solution, it is all are depending upon a pair of sinusoidal signals. So angular frequency of the both, like pair, they are given that a pair of the sinusoidal signal. So based on that, angular frequency of the both like x1 of n and x2 of n. x2 of n, where it's omega is equal to 5 pi radians per cycle. So where n is 2 pi m by omega and 2 pi m by 5 pi, it is equal to 2 m by 5. So this is this can be only for m is substituted where m is equal to 5, m equal to 10, and m equal to 15, which results in where m is equal to 2, 4, 6, okay, and so on. Okay, like this. This is related to the first one, angular frequency of the boat, where x1 of n and x2 of 2. Coming to the second bit, express the composite sinusoidal signal, where y of n is equal to x1 of n plus x2 of n. For this case, trigonometric identity. That identity is followed by a cos omega n plus pi is equal to a cos omega n into cos pi minus a sin omega n into sin pi. So here is where omega is equal to 5 pi. Then we compare that pair of the sinusoidal signal x1 of n and x2 of n are either is periodic or it is given it is the periodic. x1 of n plus x2 of n with the above equations to obtain. So you can ready to obtain that where a sin pi is equal to -1 and a cos pi equal to root 3. Okay, and so tan pi is equal to, we know that sin pi by cos pi, it is also equal to the amplitude of x1 of n by amplitude of x2 of n. So we know that a sin pi is equal to -1 by the amplitude of x2 of n is root 3. That means square root of 3 minus 1 by square root of 3, where pi is equal to pi by 6. Like this, a sin pi is equal to -1. So here by using this, user can calculate the a value, where a is equal to -1 by this value, sine of -pi by 6, because of that pi value. Since here it is the pi value, it is already that pi is equal to -pi by 6. So therefore, try to calculate from this, where a sin pi is equal to -1 from to a, where a is equal to -1 by sin pi. So like this, where a is equal to -1 by sin into pi value, we know that pi by 6, like this. So after that, we have to substitute this one, it is equal to 2. Okay, so like this, we have to evaluate this all two pairs of the sinusoidal signal for calculating x1 of n and x2 of n. Finally, the outcome is y of n. That y of n is equal to 2 cos of pi 5 into pi n minus pi by 6. If it is according to, we may express output response y of n as y of n is equal to 2 into cos 5 into pi n minus pi by 6. So now we are to verify that what is the relationship between sinusoidal and complex exponential signals, because what we want to evaluate, we want to estimate or want to observe that our signal is either CTS and DTS. So we require this type of relation between sinusoidal and complex exponential signals. The signal is, so here it is, we have to use that all signal as identity, e power j theta equal to cos theta plus j sin theta, and complex exponential signal where b is equal to a into e power j theta is required. After that, x of t is equal to a into cos of omega t plus pi. Okay, so a cos of omega t plus pi, and if it is the real value RE into B into e power j omega t. So like this, we are going to evaluate this one at B into e power j omega t is also equal to that B and A into e power j pi e power j omega t. Okay, so like this A into e power j omega pi, here it is assigned that A into e power j pi into e power j omega t. So that means A into e power j, so the common factor here j pi plus omega t. So that we are ready to calculate that this value where A into cos of omega t plus pi plus j into A sine of omega t plus pi. Okay, so like this, the continuous time signal in terms of the function, in terms of the particular function like sine function, it is followed by x of t is equal to A and A into sine of omega t plus theta, where if it is b equal to A into e power j theta, so A into sine of omega t plus pi. So here it is the previously we have seen the real term and now it is imaginary term. I am of e power b into e power j omega t. Now coming to the discrete time case, A into cos of omega n plus pi is equal to real of b into e power j omega n and A sine omega n, that A sine omega n. If it is that using this Euler, usually can identify that 2-dimensional or 3-dimensional or whatever it is. Okay, now coming to this discrete time unit step function, or we can consider unit sequence function. So it is followed by u of n, where u of n is equal to 1 comma n greater than or equal to 0, 0 n less than 0. So we can observe the term graphically how many samples are available if it is the unit sequence function n versus u of n. Okay, next come to the discrete time unit ramp function. It is followed by ramp of n is equal to n comma n greater than or equal to 0, 0 n less than 0. So here it is also equal to the summation m is equal to minus infinity to n u of m minus 1. Okay, so like this here the graphically we are right to represent that n versus ramp of n. Okay, like this some discrete time unit ramp function, how it is varies from this origin. So here it is first sample, second one, third and fourth sample. It is with this combination of this n, where it is n is equal to 4, that parallel with this ramp what do you call ramp of n here, that is because of we are in the discrete time signal. So here also it is nothing but 4, like this, where n is equal to 5 here, 6, 7 and 8. If it is where n is equal to 8, okay, the ramp what do you call ramp function it is for ramp of because of we are in the discrete time signal, it is also equal to 8. Okay, so like this go on using that n value is equal to 9, 10 and so on up to n is increases the time what the ramp of n, that is a discrete unit ramp function, is analyzed mathematically and graphically. Yeah, discrete time unit impulse function or unit pulse sequence. Here it is followed by delta of n is equal to 1, n is equal to 0. So 0 n not equal to 0 with this. Okay, so we can ready to represent that where n versus delta of n or unit pulse sequence. Unit pulse sequence versus that n value is you can identify the discrete discrete time unit impulse function. We have to consider the mathematically and graphical representation of this n versus delta of n. Okay, delta of n is also equal to the delta of an for any non-zero finite integer a. Okay, come to the unit pulse sequence. So the discrete time unit pulse is a function in ordinary sense, in contrast with the CTS. Here it is that using CTS continuous time signal or continuous time unit impulse. With this, it has a sample property based on the sampling property. So it has no scaling property. So using these all constraints, the properties based on these all properties, you can estimate that unit pulse sequence. So based on that, the discrete time unit pulse is a function in the ordinary sense, in contrast with the continuous time unit impulse. It has sample property, but it has no scaling property. That is, so where delta of n is equal to delta of an for any non-zero finite integer a. Okay, next come to the operations on signals. Already we know that all signals, based on the signal, how we are operating. Because of this, sometimes a given mathematical function may completely describe a signal based on the interpretation by using the mathematical notation or maybe graphical representation. Okay, but operations are based on with this either mathematical notation or maybe graphical or maybe different notations. But here, the operations of the signals, sometimes the given mathematical function so may completely describe the signal. Okay, describe the signal. Different operations are required for different purposes of arbitrary signals. So the operations on the signals can be we have to use that time shifting, time scaling. After that, they are using the time inversion or maybe time folding. Coming to one by one because of all it is assigned. So one is the operations on signals can be depending upon time shifting, time scaling, time inversion, or time folding. You have to see one by one. That is, you can understand that operations on signals it is varies. Okay, time shifting. The version signal is followed by x of t, is shifted by an amount of t naught. Where we know that where x of t, where x of t is continuous time signal. The original signal x of t is shifted by an amount t naught. The t naught, okay, based on that, the t versus x of t is represent that all. So it is shifted. Normally we know that t versus x of t, yeah, initially from that origin is 0. This side plus 2, where t is equal to plus 2, here is minus 2. So here x of t is 1, here it is the original signal is x of t. Based on this, shifted by an amount of t naught, how it is varies. So where x of t minus t naught. So that means the signal delayed. The signal is delayed. Shift to the right. How we are shifting the right? Because of so the signal operations are depending upon these all notations. Major one is time shifting. Here like this, using this x stands to x of t minus t naught, the signal delay shift to the right. Okay, like this. Already initially we know this one. Compare this and this. Origin is 0. The t is here it is t is 2. It is assigned, but here it is t is t naught minus 2 in place of 1 and 2 and t naught plus 2. Okay, so like this, based on that, where x of t, normally we know that x of t, where x of t versus and t is assigned from the origin here, where x of t x of t naught shifted to the right, because of it is mentioned that our delay. The delay is specified x of what do you call t minus t naught. Signal delayed plus shift to the right. Like this is, you can observe that what you call, using this all notation, the original signal is x of t shifted by an amount of t naught, where x of t tends to x of t minus t naught. Signal delayed plus shift to the right. It is ready to observe like this. Okay. Next, time shifting, where x of t tends to x of t plus t naught. Okay, signal advanced to shift to the left. Okay, shift to the left. So normally we know that our signal is like this, where t versus what do you call x of t. T is signal, the x of t plus t naught, the signal advanced, shifted to the left. Here previously we have seen that right, how it is shifted delay based on the delay, but this case it is shift left, delayed with this what you call t plus t naught. Like this it is specified, t versus x of t plus t naught. Previous one is where x of t minus t naught. Here this case t, so we have to verify that. Previously it is mentioned that t minus t naught. Here it is mentioned what do you call the t versus, okay, the t versus x of t minus t naught. Now this case, this is nothing but the original signal x of t is shifted by an amount t naught. Now coming to this case, what do you call the t versus x of t plus t naught. How it is shifted from, this is the origin, now it is shifted to what do you call, here it is, this value is nothing but t naught, what do you call, minus t naught plus 2. Here it is t naught, here it is t minus t naught to minus 2. Okay, it is somewhat, it is advanced level. Okay, now time scaling. For this given function x of t, x of a into t is the time scaling version of x of t. So x of t, here x of t, we know that one, it is the continuous time signal. Okay, with reference to this, so what do you call x of a into t is the time scaling version of this x of t. Okay, with this, for a greater than 1, so it disappeared. A greater than 1, period of function x of t reduces and functions speed up. That's why go on using this all condition. But for a greater than 1, period of function x of t reduces, what do you call, the function speeds up. Okay, graph of this function, what do you call, shrinks. How it is, where is for the, what do you call, this case where a greater than 1, now for a less than 1, the period of the x of t increases and the function slow down. Previous one, period of function x of t reduces and function speeds up. In this case, if we are using the condition a less than 1, the period of the x of t increases and the function slow down. Okay, so like this, we are verifying the graph of this function expands. Okay, say for example, given x of t, and we have to find y of t is equal to x of 2t. Using this simple example, you can understand the time scaling, how it is varies. Like this, where t versus x of t, normally from the origins to here, from 0, 1, 2, 3, 4, and so on. T is specified, x of t is 1 the time. Okay, it is given. Okay, x of if it is t versus y of t is equal to x of 2t. So the period of x of t is 2 and the period of y of t is 1. Okay, now given y of t, find that w of t equal to y of 3t and v of t is equal to y of t by 3. Using a simple example, this is given like this, where t versus y of t, is y of t is y of 3t. Okay, so y of t is 2. Like this, speed up by 3. So here it is specified that t versus w of t. Okay, if v of t is equal to y of 1 by t by 3, so it is assigned that 0, 3, 6, 9, and so on. The t versus v of t is observed like this. That you can sketch like this for time scaling value parameters. Next, come to time reversal. The time reversal is also called as time folding. Okay, so in time reversal, signal is reversed with respect to time. The time is specified, that is where y of t is equal to x of minus t is obtained from the given function. Is you can estimate the time reversal. Okay, the time reversal t versus x of t, here it is, where origin is 0, t1 and t2, where t is equal to t. Okay, now, so where t versus y of t is equal to x of minus t, So like this is I maximum. Here it is, where this point is specified minus t2. So with reference to this origin 0 and this point is minus t versus what you call with the y of t is equal to x of minus t. You can consider this on the time reversal. Now coming to the operations on the discrete time functions. Okay, already we have seen that all what you call CTS, continuous time signal, and discrete time signal. Okay, within this. So what is the operation of this all are in terms of the discrete time signal? Based on this all discrete time signal, we have to concentrate that on discrete time functions. Okay, with this. So times shifting, n tends to n plus n naught, no n naught and integer. Okay, like this it is specified n versus g of n. If it is n is equal to what do you call minus 1, g of n is equal to 1. Okay, so here it is 0, where n is equal to 0. So from here, so what it is, this is 0, n versus g of n. Okay, so here it is identified the maximum is 10, isn't it? So maximum value is it is specified from t n versus g of n. Okay, using this all numerical value n versus what do you call that n versus g of n. Okay, if it is n is equal to minus 1, the time g of n is equal to 1. If it is n equal to 0, okay, n is equal to 0, what happens that g of n is equal to 2. It is here. Okay, here n is equal to 0, it is specifying, and it is origin, n is equal to 0, that g of n is equal to, normally it is 1, no? Here it is 2. It is specified, it is 2. That is g of n is equal to 2. Next, g of n is equal to 1. Here this is the 1. Here it is 0. This is 1. 1, 2. This is nothing but g of n is equal to 3. Okay. Next, if it is n is equal to 2, where g of n is equal to 4. If n is equal to 2, this is the 2, isn't it? This is the 2 where what do you call g of n is equal to, where g of n is equal to 4, and so on. So if it is 3, 5, if it is n is equal to 4, g of n is equal to 6. If n is equal to 5, g of n is equal to 7. If n is equal to 6, here consider 2, here it is 3, 4, 5 and 6. So here it is n is equal to 6, g of n is equal to, what do you call, so 8. Okay, here it is 8. Okay, where this is 8, isn't it? And so on. If it is n equal to 7, n equal to, what do you call, 8, and so on. Here it is 8 equals to n equal to 8, g of n is equal to 10, 9 and 5 and so on. Okay, this is the time shifting. N tends to n plus n naught, where n naught is n naught and integer. Next, coming to this, n versus n plus 3, g of n plus 3. Okay, so here it is n value is specified here from this origin to 1, 2, 3 and so on, and is increasing up to 7. Okay, the time n plus 3, g of n plus 3. Like this it is specified. So n versus n plus 3, g of n plus 3. Okay, like this the operations on discrete time functions, like this, time shifting, n tends to n plus n naught, where n naught and integer value. Okay, like this. Now coming to the scaling, signal compression. Signal is compressed. How it is compressed here, where n versus, what do you call, g of n. Okay, so, and where n tends to kn. Okay, if k an integer greater than 1. Okay, so now coming to these classifications of the signal. So we want to enter this on DTS and CTS. We require some basic knowledge, basic what you call stuff is required. Classification signal. Previous videos we have seen that the classification signal. We have to recollect this all signal. After that, we enter that our DTS, in depth of DTS versus CTS, discrete time signal sampling or whatever it is. So for this, classification of the signals is followed by deterministic or non-deterministic signal. Second one is periodic and aperiodic signals, and even and odd signals. Of that we are to verify the energy and power signals. Okay. Now coming to the one by one, deterministic and non-deterministic signal. Yeah, in this case, so right to concentrate on deterministic signal, deterministic. So behavior of these signals is predictable with reference to what you call t. Okay, with reference to the time t, there is no what you call uncertainty with respect to its value at any time. So the signals can be expressed mathematically. So you can consider that, for example, x of t, you know, that continuous time signal. It is specified that deterministic signals where x of t is equal to, what you call, equal to sine of 3t is considered. This is the deterministic signal. Okay, this is the mathematical is assigned. From this mathematical, how they are represented graphically. So like this. So right, to verify this our deterministic signal. the signals are what you call signal is assigned here. Normally we know that it is before that there is we have to consider that a continuous time signal, positive half cycle and negative half cycle, and so on, cycle to cycle, and so on. If it is normally using the sinusoidal waveform and so on. But in this case, you have to identify the deterministic signal. The behavior of these signals is predictable with reference to the time. Okay, there is no uncertainties with respect to its value of any time. The signals can be expressed mathematically, or we can consider that graphically. For this case, all samples, number of samples are available here. Like this. This is the normally sinusoidal waveform. This is the positive cycle and negative half cycle, positive peak, peak to peak, and so on. But here, in terms of the deterministic signal, is specified like in this type of graphical representation. Now, coming to this non-deterministics or random signal, and compared to this one, here it is the deterministic. Like this, only positive going transition, positive half cycle and negative half cycle. Like here, positive half cycle and negative half cycle. If it is one cycle, positive half cycle, negative half cycle, you can consider that what you call based on this or what you call how many samples are available here. It is specified like this. Okay, and so on. But this case, non-deterministic or random signals. So here it is. So here the signals are available here. The sample origin only, the sample is like this, and so on. Consider this one. The sample is here, two samples. Here it is. There is no deterministic because of this the what you call non-deterministic. This one and this one. Here it is. Consider this all are non-deterministic. Okay, or we can consider that a non-deterministic signal, or maybe consider that random signal. Okay, with this behavior of these signals is random, that is not detectable with respect to time. But the previous one is you can predict with respect to that what you call time. There is a major difference between deterministic and non-deterministic. Okay, there is an uncertainty with respect to its value at any time. Already it is specified. Compare this and so on. Okay, and these signals cannot be expressed mathematically. It is possible. It is highly possible. If you are entering that all deterministic signal, there is a possibility of representing expressed in mathematical notation or mathematical expression. Okay. Say for example, thermal noise generated is non-deterministic signal. So as you can estimate, as you can distinguish between this and deterministic and non-deterministic or random signal. Okay. Next, coming to the periodic and non-periodic signals. So given x of t is a continuous time signal, and we have discussed that x of t, where x of t is nothing but what you call continuous time signal. Okay, here the x of t is a periodic. If f of t, if f of xt, it is f of, so if x of t is equal to x of t plus t naught. We know that it is specified the capital T and small t. For any t and any integer n, it is specified. But using this a simple example, easily can identify that, easily can understand the thing. Okay, so where x of t is equal to a into cos of omega t. Already is assigned x of t. X of t it is given, where x of t is equal to x of t plus t naught. Isn't it? So where x of t is equal to a into cos of omega t, where x of t plus t naught, a into cos of omega into t already it is specified, where t is equal to t plus t naught. So after t is going to simplify this, a into cos of omega t plus omega into t naught. It's not omega, it's w is equal to a into cos of wt plus 2p. So very simple that what you call x of small t plus capital T naught is also equal to this one. Okay, but here we know that all capital T, okay, that capital T is assigned 1 by f naught. We know reciprocal of that f naught, so that omega is equal to 2pf f naught. Okay, for this is you can identify periodic non-periodic signal. So one more for non-periodic. This is all nothing but a periodic signal. Now coming to the non-periodic. For non-periodic signals, x of t not equal to x of t plus t naught. A non-periodic signal is assumed to have a period of t is equal to infinity. Capital T is equal to infinity. Big example of non-periodic signal is an exponential signal. Like that exponential signal may be like this. Okay. So using this all particular signal, you can recognize that all periodic and aperiodic signal. Yeah, there is important condition of the periodicity of discrete time signal. The discrete time signal is periodic if x of n is equal to x of n plus n, small n plus capital N. For satisfying the above condition, the frequency of the discrete time signal should be a ratio of two integers. Okay, like this, that is f naught, that f naught is equal to k by n. Okay, now sum of the periodic signals, x of t is equal to x1 of t plus x2 of t. Okay, x of t plus small t plus capital T, x1 of t plus m1 into x1, x2 of t plus m2 into t2 plus x3 of what you call t plus m3 t2, so on. Like this is going to present sum of periodic signals. M1 T1 is equal to M2 T2 is equal to T naught, or you can consider M3 T2 is equal to T naught. This is the fundamental period. So this is the best example, cos of Tp by 3 plus sin Tp by 4. If T1 is specified, 2p by p by 3, 6, and T2 is 8, T1 by T2 is equal to 6 by 8, it is 3 by 8, and that means M2 by M1, it is, we can consider rational number. So similarly that M1 T1 is equal to M2 T2, to find M1 M2. So here is going to finding this same value, 6.4 is equal to 3.8, 24 is equal to T naught. Okay, so some of the periodic signals may not always be periodic. Be aperiodic, should be periodic. We'll see. We'll continue the next DTS, how it is varies this all periodic and aperiodic signals will be. So how it is affected with the DTS, discrete time signal, and so on. Okay.
Like, share and subscribe. Hit the bell icon for more updates.